Okay, so welcome to the first lecture in Fundamental Concepts in Mathematics. So, the first topic I will discuss is what we call logic. So, in logic, we will explain the term proposition. So, a proposition in logic, it is a declarative sentence that is true or false, but not both. So, a declarative sentence which is true or false, but not both. So, example of a proposition would be the statement 1 plus 1 equals 2. So, we all know that this statement is a true proposition. So, for the notation in propositions, so we will use any small letter like P, Q, R, and so on. So we denote this notation for a proposition. Now, if we have two or more propositions, mm, we will denote that by using any big letter. So this notation would be for a compound statement. So a compound statement, so we have two or more propositions. Now, in propositions, we have some logical connectives. So these are the following. We have this symbol, so we call it the AND proposition and logical connective. We have this symbol, we call it the OR logical connective. We also have this symbol, we have the NOT logical connective. And we also have this logical connective. We call it the implies logical connective. So let us discuss these logical connectives one by one. So we will first discuss the compound statement P and Q. So we call this P and Q. So P and Q here are propositions. So we define P and Q as So P and Q is said to be true if P and Q are both true. Otherwise, the compound statement P and Q is false. So to have another perspective of the definition of the compound statement P and Q, we can use the so-called truth table. So the truth table is simply a table that composed of the truth values of a proposition. So for the statement P and Q, so we have P, Q, P and Q. So P has four possible truth values. So I will write here, so true, true, false, false. And then Q, we have true, false, true, false. So by the definition of P and Q, we know that if the proposition P and Q is true if both P and Q are true. So the value here would be true. This is false, false, and false. So this is the truth value for P and Q. So next comes the proposition P or Q. So P or Q. So we define the proposition P or Q. So P or Q is said to be true if P or Q is true. Otherwise, P or Q is false. So P or Q is true if one of the propositions is true. Otherwise, we have a false statement. So to do the truth table for the proposition P or Q, so we have P, Q, P or Q. So we have true, true, false, false, true, false, true, false. So the value here is true. So for this row, we also have true, and then we have true and false. So this is the truth value for P or Q. So next comes the proposition not P. So we say that not P is true if P is false. Otherwise, P, not P, is false. So the truth table for not P proposition, we have P, so we have true, false. So not P, we have false, true. So this is the truth value for not P. And then lastly, we have the proposition P implies Q. So P implies Q is false if P is true and Q is false. So otherwise, P implies Q is true. Now let us write the truth table for the proposition P implies Q. So we have P, Q, P implies Q. So we have true, true, false, false, true, false, true, false. So by definition, the proposition P implies Q is said to be false if P is true and Q is false. So we will write here, so P is true, Q is false. So the truth value for this row would be false. And then otherwise, we have a true statement. So this is the truth value for P implies Q. Okay, so I forgot to define also some terms that we need to consider. So these are tautology and contradiction. So we call a proposition be a tautology if all of its truth value is true. So all of its truth values are true. Contradiction, so all of its truth values are false. So for the notation, so our notation for a tautology, we have T sub 0 and F sub 0 for contradiction. Okay, so let's move on to logical equivalence. So we say that P and Q are logically equivalent if P and Q have the same truth value. So for example, the proposition P implies Q is logically equivalent to the proposition not P or Q. Also, not P and Q is logically equivalent to not P or not Q. And then I will introduce to you this proposition. So we read this as P if and only if Q, and it is logically equivalent to P implies Q and Q implies P.